This is chapter 18 on air pollution, and we're going to be starting with the statistical types of air pollution. So the chemistry in the atmosphere, air is mostly made up of nitrogen, then oxygen and argon and water vapor. A material cycle through the atmosphere as they do in other reservoirs, and you can kind of do the same calculation for residence time as you can for water reservoirs as you can for air. The residence time for oxygen, about 5,000 years, carbon dioxide, 100 years, and nitrogen is particularly forever, 44 million years. And here's a picture of the carbon cycle where these various processes emitted into the atmosphere, and then it kind of mixes with rain, becomes acidic rain, comes back down where it can react with the sediments, the little critters, like kind of incorporate that into the carbon into their shells. Um, they dissolve all of that kind of thing, and it comes back up into the air through again all these processes here. So carbon cycle. Types of air pollution. Here's a graph showing particulate source. Oh, let me start with particulates. Particulates are like pretty much like dust. It's like the physical, you can see it. Well, you can see smog too, and that's a gas. But well, you think dust, and like soot or soot. Um, so here we have mostly industrial and vehicles, combustion. The nitrous oxides, we call them NOx, non-road mobile, whatever that means. All right, so gas pollutants, we have oxides of carbon, nitrogen, and sulfur. So particulates, fine grained solid particulates suspended in air, soot, smoke, ash, like from burning coal or logs or anything, dust, released from industrial processes, but also just regular dust, like little pieces of sand and silts that are picked up. Um, Other solids from burning and from 35 million tons a year from combustion to 180 million tons a year, which is mostly industrial. So that's the range that we are emitting from anthropogenic sources, meaning human. Particulates. Let's see, we've just got some graphs and maps here. Here's an image of black carbon, otherwise known as soot. I don't think I'm saying that correctly. Soot, not something you say in everyday language. Um, Showing kind of where it is, at least on this day. Here's aerosol thicknesses with the different types. So red is dust over, the desert of the Sahara. That makes sense. And we have carbon and sulfates pretty much everywhere else. And salt over the ocean, as you would almost expect. And then emissions, just generally, you can see that they have been decreasing, so that's good. Then our next type are carbon gases. And so we have carbon dioxide and carbon monoxide. So carbon dioxide is essential for the life of plants. It's what they use to photosynthesize. We breathe in oxygen, we breathe out CO2. It also comes from combustion and volcanic eruptions. It has a very short resident time, and easily fluxes between oceans and atmosphere, as we saw in that picture of the carbon cycle. Then there's carbon monoxide, and this is not very common, which is good because it's like poisonous to us. Not really poisonous. It like takes the place of oxygen in your hemoglobin in your blood. And so it's essentially, carbon monoxide poisoning. You can die from it. Um, Volcanoes, fires, lightning, and fossil fuel burning is where it comes from. It's odorless, tasteless, and invisible, toxic to humans and animals. That's why you have to have those little carbon monoxide detectors, especially if you're going to be burning gas. If you have any kind of gas furnace or anything in your home, definitely get a carbon monoxide detector or two. They're like really cheap. And residence time of a few months. Next type is sulfur gases. There's more than 97 million metric tons of sulfur dioxide, SO2, are emitted worldwide each year mostly from coal combustion, which is crazy because you kind of think of coal as being like a thing in the past, but obviously it's not, at least not globally. Very short residence time. Um, and it forms sulfuric acid when it's mixed with water, which is like the major contribution to acid rain. And it can cause lung irritation, eye irritation, and then, because it becomes sulfuric acid and acid rain, it can contribute to water pollution and, lower the pH of your lakes and things. It hurts fish and whatnot there. In all life, I suppose, trees, everything. But we've done a really good job of emitting them in this country while we still are burning coal. We do a much better job of scrubbing the emissions than we used to. But like I said, globally, this is just America. Globally, there are lots of countries still burning coal that really haven't tried to clean up anything. Next is nitrogen gases. We usually kind of put these all together and call them NOx because it's like NOx, depending on how many oxygens there are. So instead of like NO2, like nitrogen dioxide, like X. Anyways, I'm just rambling now. So can have complex geochemistry, like nitric acid here. We got the two H's in front of it, I suppose. Think trying to think if ammonia, it's got nitrogen in it. It might or may not be considered one of these nitrogen gases. Um, Oxygen and nitrogen are abundant in the atmosphere. High temperatures can cause nitrogen and oxygen to form nitrogen oxide compounds that NOx I was talking about. Um, Nitrogen dioxide and sunlight can produce photochemical smog. And then it can break down in sunlight to nitrogen monoxide and will react with common oxygen to form ozone. So that one extra oxygen takes off and then can connect with this O2, and then you get ozone. Ozone is not good for you. Ozone inhibits photosynthesis in plants and can cause severe medical problems in people in urban areas where abundant automobiles are in operation because we get a lot of our nitrogen gases from automobiles. Um, Gosh, I was gonna say something and now it slipped my mind. Oh yeah, the sunlight thing. Yeah, so that's why it really is smoggier in the summertime. If you've ever lived in like a major city or in a valley, perhaps like I used to, it's hard. The days aren't as clear in the summer for some reason. And then when things cool, well, for some reason, this is the for some reason. And then when things cool down in the winter time, the air is much cleaner. Also, the rain tends to like remove a lot of air pollution. So on a cool day after it's rained, the air is much cleaner than on like a hot summer day when it hasn't rained in a while. And so the rain removes a lot of the particulates, and then some of these um, gases as well as the gas mixes with water when it's raining, plus it's literally washing away the particulates. Um, and then on the cool days, you don't have as much sunlight to produce this photochemical smog. Oh, here's just an impact showing how nitrogen dioxide dropped during COVID shutdown because people weren't driving or manufacturing. So, I think a whole, if we all just went and lived like we did thousands of years ago, we wouldn't have a lot of these pollution problems. But really nobody wants to do that either. Near surface ozone concentration. So obviously, major cities, kind of minus. Surprised Denver doesn't have more. I guess it's got some, but I'm surprised it's not like, I don't know, like Las Vegas doesn't have any for whatever reason. Um, and again, this is near surface ozone concentration where it can harm people and plants. Now, however, ozone not near the surface and up in the ozone layer, which is looking at this graph here, it's just kilometers, miles, 20 miles, 10 miles. Okay, so from about 10 to 20 miles above the surface is the ozone layer. Now that's good for us because it filters out the harmful UV rays, particularly UVC. Um, which is the worst one for us anyways. So let's see. Oh, it looks like right here. An ozone-rich layer within the stratosphere. This is what the ozone layer is. It's between about 15 and 35 kilometers. Okay, that's kilometers above the Earth's surface. And it absorbs the harmful ultraviolet radiation, electromagnetic radiation, just to the shore. Yeah, so UV rays. So the UV rays help this chemical reaction uh, to form ozone. Ozone is O3. Normal oxygen that we breathe is O2. At ground level, it is very harmful to plants and animals. However, up high in the atmosphere, it's beneficial. The ozone hole, I'm sure you've heard of it. It's not really a hole, it's just where the ozone is very weak where it should be, and it commonly develops over Antarctica. And so, how does that happen? Hold on. Here's just some maps of ozone concentrations. And then at Antarctica, you can see it gets really low. If you look at the scale, these dark colors are low over Antarctica. And then here's different years. So 1979, not so bad. 1994, 2002 might be worse. 2021, maybe slightly better. I can't really tell. I thought it was getting better. I think the book definitely implies it's getting better. It doesn't look all that much better in these images, though. So now, how does that happen? So from um, chloride, from these chlorofluorocarbons. So it's the chlorine in these things that ultimately destroys, although also so does nitrogen. But legally, we didn't know nitrogen really kind of does the same thing, so we focused on these CFCs legally, really reduced those, helped the ozone, the hole in the ozone a little bit. But now that we know that nitrogen kind of does the same thing, that might maybe help explain why it's not completely related to our reductions. So I guess we can just find out if we start to reduce nitrogen. However, it would have to be global reduction, from all countries. Surprisingly, the reduction of CFCs was pretty much a global reduction. So like, yay, humanity. Um, Anyways, rambling again. So here's how that happens. So UV rays hit the CFC, which is three chlorine or chloride atoms with a carbon and a fluoride. The chlorine atom comes off, hits the ozone, bonds with one of the oxygen atoms. So now we have like normal oxygen and then I guess chloride monoxide atom. Um, and then when that happens again somewhere else, well, hold on. No, I was going to say that would have to, but no, it's not from it happening again. So then just somewhere comes along another oxygen atom, and then that bonds, makes the regular O2, and then this can go off and attack yet another ozone here. So it's just kind of like once it gets up there, it just kind of goes around and like attacks all the different ozone molecules, um, is why it's so dangerous. See, it only has a residence time of about 100 years. So the Montreal Protocol, that's the legal action that helped reduce the CFC emissions, ultimately signed by all 197 UN nations. That's amazing. A stipulated phase out of CFC production by year 2000. And then there's particulate pollutants, which we already kind of touched on, but I guess now we're just getting specific. So we have lead and VOCs. Lead causes a lot of like neurological issues. In fact, I heard once that when they were putting lead in gasoline, that there were like a lot more serial killers at that time, probably because of the way it messes with your brain. I didn't fact check that. That may or may not be true, but it kind of makes sense. It was used in gasoline. Somehow it made things run better. Yeah, brain damage, depression, apathy, and other psychological disorders. But here you can see that we have definitely, as we have reduced levels of lead in gasoline, then the levels in people's blood have also gone down drastically just from not breathing it. Um, and then we have VOCs, which are volatile organic compounds. Um, Major pollution of air, major component of air pollution, primarily from industrial processes. U.S. emissions of VOCs in 2020 were half of what they were 30 years ago, which is really good. And next we will be moving on to acid rain.